Hello and welcome to today's webcast. My name is Brianna and I will be your event specialist today. Following the presentation, we'll have a question and answer session. However, you can ask questions at any time during the presentation. Click the Ask a Question button, type your question in the open area, and click Ask Question to submit. We will answer as many questions as time allows. If you should need technical assistance, please type your inquiry into the tech support box on the left side of your screen and click the Send button. If you are disconnected from the webcast, you can log on again using the login instructions provided to you. If you cannot log back on with these instructions, please call support at 866-271-7592. It is now my pleasure to turn the webcast over to your speaker, Udipta Bordoloi. Sir, the floor is yours.
Thank you. Welcome, everyone. I am Udipta Bordoloi. I work for AMD in the field of GPU applications, specifically for compute. So today I'm going to talk about different optimization techniques that you can use specifically for GPUs, but I'll also touch upon a few simple CPU optimizations that you can do using OpenCL. And I'll use image convolution as an example algorithm to sort of showcase and to highlight the different optimizations that we can do using OpenCL. So before I start, I'm assuming that most of you are already, you have been listening to the webinar, to our webinar series. You know more or less what OpenCL is. You are familiar a little bit with OpenCL. I'm assuming you are familiar with programming on multi-core CPUs and also on GPUs. However, I will still go over our GPU architecture just to make sure that everybody is on the same page as far as our GPU architecture goes, because when we start optimizing, it is quite important for us to understand what the underlying architecture is. So I will give a very view, sort of the world's fastest overview on AMD GPU hardware on the AMD GPU architecture. Then I will sort of I have a few slides which show the mapping between the OpenCL terms and what actually goes on underneath the covers in our hardware. For example, what do you mean by OpenCL textures? If you do OpenCL textures, what is actually going on inside the hardware, right? So that once I do that, then I'll move over to the different optimization techniques, and hopefully we will be able to see why a particular optimization works and how that particular optimization actually works under the covers in the hardware, right? So we'll get started, and feel free to shoot any questions, but because the questions pop up on the screen, I may not be able to get to them until late or until I have finished talking through all the slides. I expect this to be one of the shorter presentations, not too much, so feel free to ask questions. All right. The contents for today's webinar would be: the first, I'll touch upon AMD GPU architecture. Then I'll talk about how OpenCL maps onto the AMD hardware. Like, for example, what are the different construction of OpenCL and what are the different hardware blocks that they actually map to. Then I'll briefly go over the convolution algorithm. I just have one slide talking about different optimizations that we can do on the CPU, and then I'll move over to optimizations on the GPU, which is actually the main focus of today's talk. So one of the things I want to highlight here is that our OpenCL implementation works both on CPUs and GPUs, in case you hadn't heard about that. So it works actually quite well on the CPU. It automatically does multi-threading. It does transparent multi-threading. If you, for example, have a 6-core or an 8-core CPU, or even let's say a 2-socket 12-core CPU, so that would give you 24 cores. So even in that scenario, instead of using other APIs like OpenMP or pthreads, which are actually already quite good, you can also use your OpenCL kernels that you have written for the GPU. They will get automatically translated and they can run transparently on the CPU. They will automatically get multi-threaded. They will use all the cores, and you can get quite good scaling with that. So the whole idea is that if you're writing a kernel and if you're doing software investment that is going primarily towards the GPU, but just in case it happens that one of the users of your software doesn't have a GPU, or maybe you just want to run the kernels on your laptop, you can do that. And it is not emulation. It runs in quite a high performance mode even on the CPU. Right. So that is more or less the contents of our webinar. So let's go over to the architecture of our GPUs. So I will focus mostly on the Evergreen series of our GPUs, which are the Radeon 5000 series. So we have the 5700s and 5800s. So this particular, the slide that I have here is about the Cypress GPU, that is the 5870 and 5850 series. So the 5870 has 20 SIMD units, which is what I show here. The 5850 has 18 SIMD units. So 2 of the SIMD units are disabled, right? So let's talk about the 5870, the Cypress, right? So the Cypress has 20 SIMDs, right? And I'm assuming you know what a SIMD is. So the SIMD is a single instruction multiple data unit. So each of those 20 SIMDs can work independently. That is, they can they will be taking and they will be executing different instructions. But within each SIMD will execute just one instruction per clock cycle, right? It'll have one instruction, but it'll apply the same instruction on many different data. Right? That's the definition of a SIMD, right? So this particular GPU, the 5870, has 2.72 teraflops of single precision. And right now, for this particular generation, our double precision rate is 1/5 of the single precision rate. So our peak double precision is 544 gigaflops. And the memory bandwidth from the global memory, not from the on-chip caches, right? The global memory that's on board, the memory bandwidth is 153.6 gigabytes per second. So I put these numbers in here so that you can get an idea of how fast your algorithm can go. For example, if you're writing a kernel, you can do let's say a quick math to figure out how much ALU that particular kernel needs, or how much memory that needs. And if you're getting close to 80 or 90 or even 80% of the peak, I'd say you are already getting pretty close there. So as far as optimization goes, that should be your target. Let's say you start getting towards 70 or 80% of the utilization, you should be in a happy place, and then it's not for all particular algorithms, but for certain ones, you can tweak it further to get maybe up to 85-ish. That should be pretty good, right? So one key thing to note is that most of the algorithms are actually, initially, unless you optimize them, they are actually memory bandwidth limited, right? So if you're running an algorithm and you're seeing, let's say, 1.5 teraflops of performance and not 2.5 teraflops as you'd expect, that is probably because you are hitting the memory bandwidth limit. So that's one thing that you should definitely keep in mind, right? Okay. So moving on to SIMDs. Each SIMD has two different types of caches. One is called local memory, and the other one is what we call L1 cache. So in terms of OpenCL, the local memory would correspond to the OpenCL local, or what we can call a shared memory sometimes, and the cached memory corresponds to OpenCL images or textures. Right? So I'll talk about SIMDs in more detail, but let me highlight this. So this is one SIMD, right? So here you have one SIMD, and the blue, this is one particular cache, which is the texture cache, and this is a different type of cache, which is the local data share. So let's move on to a more detailed diagram about the SIMDs. All right, so this is, in this particular figure, I'm showing two SIMDs. So for each SIMD, you can see each SIMD has 16 different units. So it has 16 different ALU units, right? So in the previous slide, when we were talking about SIMDs, I was saying that each SIMD will execute one instruction per clock cycle, but it can execute on multiple data. So in this particular case, for our GPUs, we execute each instruction on 16 different ALUs. So we can execute each instruction on 16 different data elements. For example, if there is an addition instruction that's going on in one particular clock cycle, the same addition instruction will execute on all the 16 different ALU units, right? So now the SIMD has 16 ALU units. These ALU units are actually VLIW units, but let's not worry about that right now. Let's just call them 16 ALU units. So we have this is the local data share. That is one type of cache, right? And then we also have the texture cache, which is the second type of cache, and I'll hit up on both. So this is more or less the diagram of the texture unit, right? The local data share is 32 kilobytes, and the texture cache is 8 KB. Right? Okay. So let's move on to the next slide. All right. So now for each SIMD, we have, I mentioned we have 16 ALU units. But what actually happens when we execute on our when we execute kernels on our GPUs is that our GPUs have quite a few pipeline stages, and because they're heavily pipelined, what we need to do is that to keep the pipeline filled, we execute the same instruction over 4 different clock cycles. So what happens is that in one clock cycle, you have 16 instructions or one instruction running on 16 different ALUs. Now the same instruction actually runs over 4 different clock cycles on 4 different batches of data, right? So we had 16 different data on one SIMD in one clock cycle. In the next clock cycle, we take 16 different elements of data. In the third clock cycle, we take 16 more, and then in the fourth one, we take 16 more. So in OpenCL parlance, when we talk about work items, you can think about each SIMD as executing 64 different work items, right? So in effect, although we have 16 ALU units in one SIMD, in effect, what will happen is that we will take 4 batches of 16, and we will in fact have sort of something like a virtual SIMD, which is 64 elements wide, right? So each instruction, in effect, will actually run on 64 different elements. That is one important thing to remember on our hardware. So if you have experience with running CUDA in NVIDIA, so this concept is very similar to what they call the warp. In their case, it is 32. In our case, the equivalent of warp happens to be the wavefront, and it is 64. It is not 64 on all GPUs. On our very low-end GPUs, it is 32. So you can check using OpenCL, but in most of our GPUs, it is 64. So now we have talked about all the SIMD or all of these 64 work items executing just one instruction. So what happens if there is a branch in the code, right? So what happens, for example, if there is what happens if there are 63 work items that have to go towards the left branch, and there's just one odd work item because of some boundary condition or something else, it has to go to the right branch, right? So what will happen is that the whole wavefront, that is all the 64 work items, will execute the left branch, right? And that one particular work item which is supposed to go to the right branch, it will be masked. After we finish the left branch, we'll go back to the start and we'll execute the right branch for all of the 64 work items. But now in this case, 63 of those work items have already executed the left branch. So we'll just mask them. We'll not write anything to them. And the one lone item which was executing the right branch will actually now get executed. So you can imagine that we have in our code, if we have branching, we have the left branch and the right branch. So if if all the work items have to go in one direction or the other one, we do not have any issues. Like this is the same for our GPUs or any other GPUs. But if our work items, if during execution, within the wavefront, some of the work items have to go to the left branch and some other ones have to go to the right branch, then we will need to execute both paths. Right? So if you are wondering why maybe your kernel is taking twice as long, if your whole kernel is divided into left branch and a right branch, that may be because some of the threads, or maybe even just one thread, is executing one side and all the other threads are executing the other one, right? So this is something that you need to remember when coding. This is only important if you have a lot of branching and if ALU performance becomes a bottleneck. But otherwise, you'd not need. You just need to keep this in the back of your mind. This is not such a sort of a performance bottleneck, right? Okay. So now, how does this translate to OpenCL? In OpenCL, you have this concept of merging work items into a work group, right? And so when coding for our GPUs, you can have work group sizes of 64, 128, or 256. So that is equivalent to having one work group, one wavefront, two wavefronts, or four wavefronts per work group, right? So if you have a work group size of 256 in OpenCL, that will translate to 4 different wavefronts on our hardware, right? And it so happens that if you create a work group in OpenCL, all the wavefronts that belong to that work group will execute on the same SIMD. So if you have a work group, let's say if you use a work group which is not a multiple of 64. Let's say you have a work group size which is 32 or which is 96. Right. Now that does not translate very well onto our hardware because if you use a work group size of 32, our wavefront size is 64. So only half of the ALU is being utilized. If you have a work group size of, let's say, 96, that translates to 1.5 times our wavefront size, right? So we'll have one wavefront and another half wavefront. So it's still there are ALU cycles that go underutilized if you have a non-64 multiple of work group size. So you can have work group sizes which are, let's say, 8 by 8, which is 64. You can do 8 by 16, which is 128, or you can do 16 by 16, right, which is 256. You can also do something like 256 by 1 or 1 by 256. It depends on how you want to arrange your algorithm or how you want to subdivide your whole execution domain into different work groups. Okay. All right. Moving on to the next slide. So this is the OpenCL view of the AMD GPU. So how do the different OpenCL terms translate onto our GPUs, right? So OpenCL constants go to our constant cache, and our constant cache actually lies in they are not on chip. We have small constant cache on chip, but they actually come from the global memory, right? We have work groups, and as I mentioned earlier, work groups map onto SIMDs. So all the wavefronts, if your work group is larger than a wavefront size, all the wavefronts in one work group will go to one SIMD. Image cache. So when you use OpenCL images, the data from OpenCL images are cached, and they get mapped onto this particular 8 KB cache that we have on our GPUs. Global memory is outside of the chip on the board, so it is a high latency memory. And we have local memory, which is a user-defined cache, or which is a user-enabled cache. So when you use __ local in OpenCL, that gets translated to this particular piece of hardware. Right. Okay. And then this is the L2 cache that is sort of almost transparent to you. So the image path, when you use OpenCL images, they go to L2 and then they go to L1. Right? So let's now look at the same thing from a reverse angle. This is the if you have looked at OpenCL before, you have seen this many times, the different the memory hierarchy in OpenCL, the different kinds of memory that you have. So this is sort of the reverse slide compared to the previous one. Where does OpenCL private memory reside in? It resides in the registers on our GPUs. Sometimes they may also be pushed back to what we call this LDS, the 32 KB LDS that we have, right? The work item. The work item goes to the thread processor unit, which is one of the 16 ALU units per SIMD. Right? The compute unit. The whole compute unit maps onto the SIMD, right? So when you have an OpenCL work group, that maps onto the OpenCL compute unit, which happens to be our SIMDs. What about local memory? Local memory maps to the 32 kilobytes of local data share, and the global memory happens to be the onboard memory, which may be 1 gigabyte of memory or 2 gigabyte, 1 GB RAM or 2 GB RAM that we talk about, that we have on the boards. That is where the global memory resides. Right? All right. So this is the view this is more or less our GPU architecture and the OpenCL mapping onto our GPU architecture. So keep this in mind always, and then if you have doubts when writing OpenCL, refer back to this so that you have a very good idea of when you're writing a kernel and when you're using different pointers and different blocks of memory, you will have an idea of how fast that memory is, where in the particular where in the GPU that particular memory resides, so you can know how fast or how slow that memory is. Okay. Now, moving on to the next stage. So this is going to be, I'm going to very quickly go over the convolution algorithm. It is the simplest algorithm in the world that we could use for this particular webinar. I'm sure all of you have used it or heard about it. So if not, I'll just go through a very brief overview, and then I'll just take a quick small detour. And since I mentioned CPU, I have one slide where I'll talk about how to do optimizations on CPU, which coincidentally is not different from the optimizations that you would do for the GPU, right? And then we'd move on to the real thing that we are here for, the optimizations on the GPUs. All right. So what is convolution? Convolution is, in convolution, you can do convolution on many different types of input data, on 1D signals, on images, and even on 3D data and so on. I'm just taking the example of a 2D image. So you take an input image, right? A 2D input image, and you take a mask. Now, a mask or filter. Now, the mask or filter just happens to be some weights. And the filter can be, let's say, 3 by 3 or 16 by 16 or whatever you choose to be. Now, what you do in the algorithm is that to get the output, you place the mask over the input image centered at different pixels. And whenever you place the mask, you take a weighted sum of all the neighbors of the pixel at the center, and the weights being the weights in the filter. You do a weighted sum, and that becomes your output. As simple as that. Right? So basically for each output image, for each pixel in the output image, all you are doing is a weighted sum over the neighbors. Okay, moving on. So for every pixel, it is basically a nested for loop. Like, right? For all the neighboring pixels across, in my case, if I have a 3 by 3 mask, right, we go over for all the 3 rows and all the 3 columns. Right. So it's a double nested loop, and all we are doing is we have a sum, and the sum is a weighted. It's a weighted sum. So these are the weights, and these are the neighboring inputs, right? And so all we do is that we say output is equal to the is the sum total of the weighted products of the weighted values of our input, right? Okay, so here's the key thing. For a 3 by 3 filter, we are doing 9 reads from our input and 9 reads from the filter, right? So this is what we need to remember for our convolution algorithm. For large filters, like for example, if we have a 16 by 16 filter, we have 256 reads from the input image and 256 reads from the filter. And so we are doing 256 reads and 256 reads for every write. So what is happening is that this is becoming a heavily memory bottlenecked algorithm, right? We spend a lot of time doing reads. Now the key thing is to note that as you move around the mask, there's a lot of overlap between neighboring pixels, right? So for example, if you have a 16 by 16 filter, and if you move from one pixel to the next pixel and you move the whole thing by one column, so of those 256 pixels, only 16 are new, right? Everything else, all the other reads are the same. So at some point of time, the optimization will involve reusing this particular data. Right? Okay, so now we'll move on to let's move on to the CPU optimization. So you remember the particular algorithm we had. This was our algorithm, right? For all the rows and for all the columns, do a weighted sum. Now what can we do for CPU? First, unroll loops, right? The second one is at compile time. So the nice thing about OpenCL is that when you're running an algorithm, you can do a just-in-time compilation for the OpenCL kernel. That is, the OpenCL kernel can be compiled at application runtime, right? So I call it application runtime, but OpenCL compile time. So because it's application runtime, you may be able to pass in the filter width, pass in how wide the filter is, how wide the input data is, pass in many different parameters that you have at application runtime, but at OpenCL compile time. So because you are compiling at runtime, you can pass in a lot of hash defines into the OpenCL kernels, and that helps. And of course, the final one would be to use vector types. So if you use vector types, for example, if you use int force or float 8s or whatever have you. So if you use 128-bit vector types, right, or I shouldn't say 128-bit, if you use 4 wide vector types, that gets translated into SSC, and it gets translated into SSC for both AMD CPUs and Intel CPUs. Doesn't matter what CPU you have. And because it gets translated to SSC, we will have SSC, and we will also have multi-threading, right? So it actually gives you a very good performance because of SSC and multi-threading combined together. Because otherwise, sometimes if you just write a for loop, for example, if you write a for loop in GCC or in Visual++, quite often it does not do auto-vectorization, and it does not spit out SSC instructions in the backend, right? So these are the three very quick things that you can do for doing optimization on the CPU. I have a tutorial up on the web that you can go look at for further details if you are interested. The whole idea is that the same optimizations that we will end up doing for the GPU will also help on the CPU, and it can make your CPU implementation faster than doing multi-threading using OpenMP, for instance. So here's an example, right? So the red line is a multi-threaded OpenMP implementation of the convolution algorithm, and then I just have two different implementations of our kernel on the CPU. One is using vectorization. It has float force. The other one is using vectorization, and also I pass in hash defines different values, like for example the filter width and then the loop limits during runtime. It's runtime, OpenCL compile time. So you can see that we can get up to twice the speed of standard multithreading using vectorization on the CPU, right? Okay, so let me see how we are doing on time. All right, I think we are okay. All right, so now finally we come to the interesting part, which is optimizations on the GPU, right? So let's remember now, I want to go back and reiterate what we have on our SIMDs, right? Because this is quite important, right? Let's see. The two things I want to highlight are, yes, all right, image cache and the local memory or the user cache, right? You remember when you talked about the convolution algorithm, I said that there's the potential for a lot of data reuse. For example, if you have a 3x3 mask, and then you calculate the weighted sum for one particular location, you move the mask to the next location. So let's say you shift the whole mask by one column to the right. So 6 of the 9 elements that you have already read can be reused in this particular step. Only 3 of those elements are new. So the whole idea now is that how we can reuse the data. And to reuse the data, we will have to reuse data from cache. So once the data is loaded onto cache, we'll try to reuse it as much as possible. So we'll explore both paths. We'll try to use the image cache using the OpenCL images route, and we'll try to use the user cache, which is using the OpenCL local memory route. Right? Okay. So let's go back to the GPU optimizations. Right? All right. First, let's talk about a naive implementation. Naive implementation, as in, I just replicate the very simple nested for loop that I showed you for the CPU. Right? It is exactly the same as the CPU, except that in OpenCL, all you need to do is get the output ID, right? You'll say what is the X location and what is the Y location of the output ID, and then do a weighted sum and then write it out, right? So the meat of the kernel, which is the 2 nested loops, remains the same. So for our webinar here, we'll take this particular examples. We'll use a 16x16 filter. We will use a 4K by 4K output image, and for this 4K by 4K output image, what we need is a 4K plus 15 and a 4K plus 15 input image, and we need this input image to be a little bit larger because the mask actually overhangs. So when we put the mask at a location on the output image, so the mask needs neighboring pixels, and when we put the mask at the corner pixel of the output image, you can imagine that the mask extends a little bit outside of the output image, which is why we need a larger input image. We can do things with borders and replication and etc. but I just want to have an input image with borders because our focus is not on the use of or how to do convolution better, but our focus is on optimization, right? Okay. So we have a filter which is 16 by 16. We have an output image which is 4K by 4K, and our OpenCL workgroup, I will start with a workgroup size of 64 because that happens to be our wavefront size, right? We need a workgroup size to be at least 64 and to be multiples of 64 for good performance on our GPUs. So if I do that, it takes on Radeons, one execution of the kernel takes 1500 milliseconds, so 1.5 seconds. Right? All right. So one thing I haven't mentioned on these slides is how to actually do timing on OpenCL. So to get a good timing, like if you're just interested in timing, right? If you're just doing benchmarking and not actually using the algorithm in a pipeline along with many different other kernels that you might have, what you want to do is that you want to enqueue the kernel a lot of times. Let's say you enqueue the kernel 100 times or maybe even 1,000 times. Right? You say you do CL kernel, you set parameters, like you set all the kernel parameters, and after you are done with everything, you call CL finish just to synchronize the pipeline, just to make sure your pipeline, everything is empty, just to make sure that the GPU has done everything it needs to do till that point. After you call CL finish, you know that the GPU is fresh, right? And you can start timing. So after you do CL finish, you say timer start. After you say timer start, you can do in a for loop CL enqueue and derange kernel for let's say 100 times or 1,000 times, right? You just say enqueue and keep doing it. After you have done all the enqueues, you can call CL finish once, right? After you call CL finish, then you immediately take the time. So what you are essentially doing is that you are calling 1,000 NQ kernels, and then you are calling one CL finish, and then you are taking time. So this gives you the closest possible approximation of how fast your kernel is going. Now the reason, what is the other thing that you can do? The other thing that you can do is that when you call the kernel, let's say inside the for loop, you can say CL NQ range kernel, and then you can call CL finish both inside the for loop. So NQ range kernel, CL finish. NQ range kernel, CL finish, right? What happens in that case is that CL finish takes some time of its own, right? And if you do that, if you call CL finish in every iteration, you'll also be measuring CL finish time. So we'd not want to do that. I mean, you may want to do that, but I just want to distinguish the two different scenarios for you. So in one particular scenario, you are measuring both the kernel time and the CL finish time. In the other scenario, you are measuring the kernel time as much as possible, right? So ideally, if you want to just take the kernel time, call it 1,000 times, NQ the kernel 1,000 times, and then call CL finish once, right? Okay. So that is how I measured. That is how I measured this particular time. That is 1511 milliseconds for the very naive kernel without doing anything. Okay. Moving on to the next slide. Let's try our first optimization. So as I mentioned, the immediate thing that stands out is that we are not reusing data, right? In the naive kernel, we are accessing everything from global memory, and we know that it is not cached. By the way, that is very important for you to remember that when you have a global pointer, let's say _ global float pointer, it is not cached. For example, this is not cached, this is not cached, and this is not cached. None of these are cached. So what happens is that even if you are accessing the same element 20 times or 30 times, that same element, if it is not cached, will be accessed 20 times or 30 times from the global memory, which has a very high latency. We do not want that. So our first step is to put them into what we call LDS on our hardware, and in OpenCL parlance, what is called as local memory. In CUDA parlance, it's called as shared memory, right? So if you want to do the math, for every output pixel, we were fetching 256 input pixels, and we are not even talking about the filter. We are not even talking about the mask weights, right? We are just talking about the input pixels. So what we'll do is that we'll share the input data within each work group, right? Now this is important. So we can only share data within a work group, right? That is what OpenCL says, that when you use _ local, that particular pointer is shared inside a work group. And why does OpenCL force you to do that inside a work group? That is because the hardware that gets mapped onto local, the hardware which is LDS, which we call as LDS, is unique for each SIMD. So each SIMD has its own LDS, right? And one SIMD cannot really access LDS from another SIMD. So if I'm a SIMD, I have to access my own LDS, right? So what happens is that when you have a work group and when you use local, the whole work group maps to one SIMD, and this local maps to the LDS, the particular LDS on that particular SIMD. So what we're going to do is that we'll put all the memory onto the local pointer, which would be LDS, and then we'd start accessing the memory again and again repeatedly from that local memory. So let's say if our work group is 8 by 8, right, and our filter is 16 by 16, so now we know that the output image that we are going to spit out from this particular work group is also 8 by 8, because for the 8 by 8 work group, we have 8 by 8 work items, which is 64 work items, which will be 64 pixels on our output image, right? So the input image that is loaded onto the LDS, if you have an 8 by 8 output image, the input image that you need is 8 plus 15 times 8 plus 15, that is 529 values, right? So you can see instead of 256 values, you have 529 values. Oh, sorry, my bad. Now this was 256 values for each pixel, right? So in the naive kernel, what we are doing is 256 times 64 for the whole work group. Now in this case, we are just doing 529, right? So we have reduced the number of we have reduced the input items fetched per output pixel to 8.3. So it went straight from 256 to 8.3 per every output pixel. So this is a massive reduction in the number of input pixels that we are reading, right? So as soon as we do that, the convolution time goes from 1500 to 359 milliseconds, right? Voila, that's like a four times speed up, right? Okay. Moving on. Now, we have seen that we can reuse data from the reuse data from the neighboring pixels, right? So we were using a 8x8 work group. Now, what if we use a 16x16 work group? There will be more data reuse, right? So we are going to try to increase the work group size. So the largest work group size that we have on the GPU can be 16x16. The largest on the CPU is 32x32. Right? Okay. So we'll say let's use, instead of using a work group of 8x8, let's use a work group of 16x16. Right? All right. So somebody asked, what is the global work group size? The global work group size in this case is 4K by 4K, which is our output image, right? So we have 4K by 4K output pixels, and I just decided that one work item per one output pixel, so we'll have 4K by 4K work items, right? So that is our global work size, and we divide the global 4K by 4K domain. In the previous slide, we used 8x8 blocks, 8x8 work groups. Now in this slide, let's try using 16x16 blocks. So if it's 16x16, so filter is 16x16, right? The work group size is 16x16. So the input image that needs to be loaded is 961, right? So the output items, or the input items fetched per pixel is actually 3.7. And as soon as we do that, the convolution time reduces even further to 182 milliseconds, right? Just 3.7 items that we read from global memory, and we get a convolution time of 182. Compared to the previous slide, 8.3 items read per pixel, 359. Compared to the previous slide, 256 items read per output pixel and 151 milliseconds, right? So the first optimization that we did was put data into LDS so that we start reusing it. The second optimization that we did was that we knew that, hey, if we use LDS, why not make the work group size larger? Because that will enable more data reuse. So we decreased the speed even further. So this was about LDS. Now moving on, let's try the other caching method, which is texture cache. So when you use local memory or when you use LDS, what happens is that you need to write code. You need to first read data from the global memory and store it into local, and then you yourself start using the local memory, which is why I called it user-managed cache, right? It is up to the programmer. The programmer loads data into LDS, the data remains there, and then you start using the local memory, right? What if you do not want to go into all that trouble? What if you want to just say, give me the best cache that you can, and I don't really want to write code for local memory? So what we will do is we can use the OpenCL concept of images. So if you use OpenCL concept of images for the different workgroup sizes, here's what you get. For 8 by 8, you get 346 milliseconds, and for 16 by 16, you get 207 milliseconds. So again, both are very close, both are similar to what you use for LDS, right? And the whole idea is that you are using the concept of OpenCL images. OpenCL images are cached, right? Okay. Moving on. So now we did that, right? We did LDS, we did workgroups, and we did images. Now let's go back to the naive algorithm. Like that was trying to take care of data reuse. Now let's try to think about some other optimizations. Right. So what about the filter array? The filter itself is 16 by 16, and it is not cached. We have been reading the filter again and again from the global memory. That is also not optimized, right? So what we can do is that we can try to cache the filter. So we have two options. One is that we use the automatic caching that is provided by OpenCL images, right? Or we can use the constant buffer. So how do we use the constant buffer? To use the constant buffer, when we say underscore underscore constant instead of saying underscore underscore global, and we have to say for our GPUs right now, we have to say what is the max size. If our max size is less than 64K bytes, then it's good. We cannot right now support more than 64K bytes. So in this case, my max size is just, let's say, less than 4K. So which is fine. It goes to constant memory. So what happens if it goes to constant memory? So if it goes to constant memory, if all the threads are accessing the same element, it gets cached. So if work item 0, work item 1, work item 2, all of them are accessing filter 0 at the same clock cycle, it gets cached, right? Better than before. So what happens is that in the naive implementation time, we had 1511. If we cache the filter, remember, we now went back to the naive one. We are not using the data reuse of local and texture. Even in the naive one, we see some data improvement. We go from 1511 to 1375, right? Okay. That was optimization 4. Moving on. Let's try something else now. Let's try unrolling the loop, right? So why should we try unrolling the loop? Because it reduces control flow overhead, right? Doing any kind of loops, it has a certain overhead of its own on the GPUs. So it reduces the loop overhead, and on top of that, what we can do is that we can now fetch 4 floats, 4 input data at once. Instead of fetching just one input data, like if the for loop executes over one input item at a time, we access one input data and then another input data in the next iteration and the third data in the next iteration. So in this case, what we'll do is we will just we unroll the loop by 4 times, and we access 4 different elements of the input data at once. Now that helps because accessing 128-bit data is faster than accessing 32-bit data, right? So accessing as float 4 is faster than accessing as float, right? So that should give us better performance, and it does. So if we just do the unrolling, we do unrolling, and we fetch as float 4 instead of float, we go to 401. A drastic speed up, right? On top of it, if we say we make our filter fetch also float 4, we go to 389, right? So I'm just doing this to show that if you're accessing as floats, and if you can change your kernel so that instead of floats you can access as float 4s, you can achieve, in most cases, right? There's no guarantees. Sometimes it backfires, but in most cases you can see a speed up, right? This particular speed up is due to both. It's due to loop unrolling, like getting rid of the loop overhead, and also doing the float 4, doing the 128-bit accesses. All right, moving on. So hold on, a quick recap. What did we do? In this one, optimization 4, we used the constant buffer. In optimization 5, we did unrolling, right? Okay. Optimization 6. What if we do both 4 and 5? right? Let's try both 4 and 5. When I tried both 4 and 5, it went to 680. Well, that's not good, right? Because we were already at 389. Now, we were already at 389, and it should have increased even further, but that didn't happen. Why? Because when we did constant float, it increases the ALU usage. Now, here's a key point. Till now, ALU was not the bottleneck. Till now, memory access was the bottleneck, right? We were doing a lot of memory access. We were doing redundant memory accesses, and they were killing us, right? As we started speeding up the algorithm, and as we started using caches more and more, and as we started doing float for accesses, we unrolled the loop. We made things faster, right? Now, memory accesses are becoming less and less of a bottleneck. And now, if I say constant float pointer, it increases my ALU usage. If you look at the ISA, which is the assembly, you will see in the assembly that it increases quite a bit, right? So, all right, looks like I have 10 minutes left. I just have a couple of more slides to go. All right. So, what can we do? Now, the reason there is a ALU increase when we use constant float is that the compiler has to now, it fetches 128-bit data. It fetches float force, and then now it has to do some math to figure out which particular float you wanted from that. So it has to do sort of the indexing math, which is what contributes to the ALU usage, right? And it has to do this indexing math for every fetch, right? For every filter, for every filter multiplication, every weighted multiplication, which is quite a lot, right? So instead, if we use a constant float 4, it gets rid of all the ALUs, right? It gets rid of all the ALU math, and now this is what we expect. We see 346, right? Which is fantastic. We started from 1511, and we reached 346 by doing all these other optimizations, right? Okay. So let's try everything else now. We start from naive implementation, 1511, right? And I have the results for both LDS and textures. So we do data reuse, we get to 182 or 207, right? We use constant float 4. On this one, we get to 190 and 160. You do optimization 5. From 190, you go to 90. From 160, you go to 130. You do float 4, which is a slightly better optimization for number 5. Go to 83 and 127, right? And then you do the constant, which is the bad case that I showed. It increases slightly. It increases by a lot, right? And then you go to the final optimization, which is the good one. You go to 71 and you go to 93. So remember, we started from 1511, and we started from 4 digits, and we went to 2 digits now, right? Okay. So let's see what else we can do. Now, I talked about this on the CPU side. So when you're doing OpenCL, the nice thing about OpenCL, you can do just-in-time compilation, that you are running the application. Somebody says, oh, what kind of filter do you want to run? I want to run a 7x7 filter. You can pass the value 7 inside the OpenCL kernel if you want to, at application runtime, at OpenCL compile time, right? You can do a lot of those things. You can pass in all sorts of values that you think are constant using hash defines. Why do you want to do that? You want to do that because if you do that, our compiler, the driver compiler, can do a very good job of optimizing things out. If it gets constants, for example, it can unroll the loop to the best of its ability. It knows a lot of things. It can create defined pathways statically. It can do a lot of static compilation things that it cannot otherwise do if you pass in variables, right? How to do that? When you compile a kernel, you pass in the -d option. -d define, let's say you have filter width, right? -d filter width equals 16. You pass in that string, it gets compiled, right? So you can pass in filter sizes, you can pass in workgroup sizes, you can pass in whatever is available, right? So what happens if we do that? Okay. Now, if we do that, take a look at these. It goes to 69, 25, 68, 66, 26, and finally it goes to 25, right? We started from 15. This is almost 100 times speed up from where we started. If we use textures, notice that all of these are 128, 127, 127, etc., right? And in final one, when we do constant float 4, it goes to 63. What does this tell us? It tells us that in the texture case, for textures, it has become ALU limited. When you pass in the hash defines, right, using textures gets it caching, and it gets ALU limited. Like it gets ALU limited, and then it remains ALU limited for a while until you pass in the constant float 4, when it goes to 63. Right? So this is an example where all the optimizations are not helping because we need to do ALU optimizations, or we need to do some other optimization at this point, right? Okay, so that is all we have. Basically, we started from optimization. We did optimizations on LDS, optimizations on workgroup. We tried to use textures. We tried to unroll the loops, right? We tried to do fetch force. We tried to make the filter. We tried to use a constant buffer, and finally, we tried to use hash defines. So that's all the optimizations that we have. If you need the slides, these will be up on the OpenCL zone. We'll have a bunch of other. We already have a bunch of other training and slide materials, and then we keep updating OpenCL zone quite a bit. So keep coming back. And let me quickly go through the questions now. All right. So yes, somebody asked about code snippets. So I will try to make the whole source code for these available on the web. So give me some time. I will need some time to clean it up and post it on the web. I already have the tutorial for optimization on CPU, and I will try to do the same thing. I'll try to create a tutorial out of it and then put it on the GPUs. A tutorial for GPUs and put it out on the web, the whole source code. Right. Do you use vectorization on the Radeon? Yes, I use vectorization. So optimization 5, right, when I talked about unrolling the loops. So I did not use vectorization till that, but when I did the optimization, what I did, or when I did the loop unrolling, I unrolled by 4. So now when you unroll by 4, inside the unrolled loop, you had four weighted products. So you had the filter times input image, right? So you have that filter times input image 4 times. So what I do is that put the input image into a float 4, put the filter into a float 4, and multiply. So that was what optimization 5 was about, right? Okay. When you say global pointers are not cached, are you only referring to L1 cache? Is L2 cache used for both images and buffers? No. So right now, in our particular SDK, in what you have right now, if you have a global buffer, it is not cached at all. No L2 cache, no L1 cache. We are trying to come up with some optimization so that if it's a read-only buffer, it will get cached, but we are not there yet, right? It will come up in a future release. For now, if you have global pointers, they're not cached at all. If you have images, they're cached through L2 and then to L1. So you never actually see L2 and L1. I just wanted to show it to you so that you understand what is going on, right? So that is what is going on. Yes, images are always cached, no matter what channel order and channel data are used. Images are always cached. But beware, though, that the SIMD runs many different wavefronts, right? And the cache is actually very tiny. So the cache only helps if you access very neighboring elements. If you go to random access, then caching the effects of caching go away. On the CPU side, how do you define the constant filter? Yes, I just pass it as a normal float. Yep. So for the CPU side, on the slide I have the link, and then you can also get the link. If you just do a image convolution OpenCL search on Google, you'll see my tutorial, and you can download the source code. And it's very nice, actually. It's for beginners. It's a step-by-step tutorial. You can see what changes I do from each step to the next step. It should be very straightforward for you. All right. GPU memory stays the same between kernel launches and after CL finish. The onboard memory remains the same. Registers, local memory do not remain the same, right? Global pointers, __global, and images Like OpenCL buffers, the buffers that you create with OpenCL remains the same, yes. For the loop unrolling, by a factor of 4, do you do it manually? I do it manually, by the way, right now. We're going to release a new version of OpenCL very, very soon. We're going to release SDK 2.3 very soon, and in 2.3 there's a loop unroll pragma. So you can say hash pragma loop unroll something, and it will unroll the loop for you. So it will make it much easier for you, right? Okay, local workgroup size, because 4K by 4K is a huge number. Yes, so 4K by 4K is the global size. It's not the local size, right? The local size optimization 1, local size was 8 by 8. Optimization 2, local size was 16 by 16. And that is the max that you can do in OpenCL right now, right? So I think that is it. And the last question, I'll take the last question. Okay, direct compute allows 1024 thread size. Should we use direct compute? Yes, direct compute uses that, and then we are trying to we are taking a look at what we can do. So there are many advantages and disadvantages for doing that. For example, when you increase the work group size, what happens is that you decrease the number of work groups that can simultaneously run on a SIMD, right? So what happens is that, again, I'm going back to architecture. When you run things on one particular SIMD, one particular SIMD has the capacity to run many wavefronts. How many wavefront it runs depends on the workgroup size, it depends on the register count, and it depends on the local memory size, right? For example, if just one wavefront takes the whole local memory on the SIMD, which is 32K, then you cannot run any more wavefronts because just the first wavefront took up all the local memory, right? Similar thing about registers. If one wavefront takes up a lot of registers, you cannot run more wavefronts. Now, why do you need more wavefronts? You need more wavefronts to do latency hiding, to hide memory accesses. So what happens is that one wavefront is trying to do memory accesses from global memory. Another wavefront can come in and do ALU on the same SIMD, right? So there is a trade-off between all these different optimizations. So if you start increasing workgroup size, if you start increasing the amount of local memory that you are using, if you start increasing the amount of registers that you are using, then you will start decreasing the number of wavefronts, and that may have an adverse effect on the optimization, right? So I think that's the last question that I can take right now.